Hi, this is Mr. Swanson, and today we're going to go through the second lesson. Hi, this is Mr. Swanson, and today we're going to go through the second lesson in stoichiometry about limiting and excess reactants, as well as percentage yield. So you can see the changes. It's note 7.2, not 8.2, as in your student copy of the notes that you should have downloaded, and you should follow along with us and try to pause the video when you can and try the problems on your own. Before we get into the calculations, we want to establish a shared vocabulary. And the two main words you need to know now are the limiting and excess reactant. And so we're going to think about this as two reactants in a chemical equation, but these ideas could be extrapolated to having 3 or 4 reactants. So the limiting reactant is the one that is used up first. Okay, so that's really what you want to think about when we say limiting reactant. You want to think about the one that is going to be used up first. And what's important about the limiting reactant is that it's going to determine, okay, how much product you actually can make. So it's the one that gets used up first that determines how much product is made. The excess reactant, on the other hand, is not completely used up. So, like the word says, there's extra at the end. So that's excess. Okay, and so we are going to have leftover, and then we can think about, okay, well, with that leftover reactant, could you add more of the other reactant? So these are both very important terms we need to think about. So used up first or extra. Let's start with a non-chemistry example, and let's imagine somebody's getting dressed, and this is what they wear every day, which is a great outfit, by the way. And we want to think about how many outfits does this person have? Well, a person wears a shirt and 1 pair of pants at the same time, so here's an outfit, and here's an outfit, and then all of a sudden, we're out of pants. So pants are the limiting reactant. And we have t-shirts left over, so they are the excess reactants. So it was the pants that determined how many outfits that we could make and the t-shirts we had left over. Food is another classical non-chemistry example when we're learning limiting and excess reactants. So, you've probably made a hamburger before. Let's imagine we need 1 slice of tomato, and 1 piece of cheese, and 1 pair of buns, or 1 set of buns, and 1 burger. Okay, how many can we make? Well, you can see that these hamburgers are used up, and so we have all of this excess reactant. So in this case, we have 1 limiting reactant, and that determined how many things we could make, how many products we could make, so 3 and 3. And then we had all of this stuff left over. And the limiting and excess reactants are super important in real life. You want to think about, well, why would a restaurant have hamburgers as the limiting reactant? Well, hamburgers are probably the most expensive thing. And so because there's no way to get the perfect right amount of ingredients, you want to make sure you have extra of the cheap and expensive one, and the one that runs out first is going to be the most expensive one. So you can think about this in almost any type of manufacturing, but it's really common in the food examples. So now let's dive into the chemistry. So we're going to follow very similar procedures to what we've been doing with stoichiometry. But in this case, we're going to be telling you one of the reactants is going to run out first. So in the previous problems, you might have seen it say like we have sufficient or plenty of oxygen, saying oxygen is not going to be a limiting reactant. But in this case, we're telling you we have 6 moles of pentane and 18 moles of oxygen, and we want to know which one is going to run out first. And so also with that, how many moles of carbon dioxide can we produce considering one of the reactants runs out first? Okay, so we're going to look at these 2 pieces when we solve this. Now, to solve it, before we actually jump to the math, let's just think about this for a second. You are going to be doing this problem twice. First, you're going to be thinking about just the 6 moles of pentane, and you're going to be trying to figure out how much carbon dioxide can be produced. Then you're going to say, okay, and so the first time you're just assuming there's plenty of oxygen. Then the second time you do it, you assume there's plenty of pentane, and you're going to say, okay, if I have 18 moles of oxygen, how much carbon dioxide can be produced? And then you're going to compare those two values, okay? And the one that produces the least amount of product is the limiting reactant, okay? And that's the one that's going to determine how many moles of carbon dioxide can be formed. So that's just talking out the problem. Let's try to use stoichiometry to solve that. So here it is. And this same example could be done with grams to grams, but really, since it's just a comparison, we can stop at moles. We don't need to figure out how many grams of carbon dioxide can be formed right now when we're looking at the limiting reactant. You can just use moles to compare them to figure out the limiting reactant. So here we have the starting values that we said in the previous page, and we are using the mole ratio from the balanced chemical reaction. And here we get 18 moles of carbon dioxide can be produced, and here we get 10.8 moles of carbon dioxide to be produced. Well, the question is, which one is the one that limits how much CO2 can be produced? And that's the one that produces the least amount. So in reality, oxygen, in this case, was the limiting reactant. It produced the least amount of CO2. The excess reactant was C3H8. And so how many moles of CO2 were actually formed? Well, 10.8 moles. Because that came from the limiting reactant. Now you could go one step further now and turn those moles into grams or liters, but for now that's all we're looking at. So these problems are a little bit longer, so obviously we're going to have you do less of these problems because each problem requires you to do more. And in this case, again, we're not getting to the point where we're starting with grams and going to grams. We're just starting at moles, okay? And so the first thing you want to do, and I want you to pause the video and try it on your own, is figure out which is the limiting reactant. And so you're going to take, and you're going to start with 1.56 moles of Fe, and you're going to start with 0.899 moles of O2, and you're going to compare those to the product. Now, in this case, there's only one product, but in reality, it doesn't matter. If there are two products, you just have to compare them to the same one. Okay, so in this case, it's easy. You're going to compare them to iron oxide, but if they don't ever tell you which one to compare it to, it doesn't matter. Just pick one of them and stay consistent. So pause the video and come back and check your answers. Alright, so doing the problem, we compared both reactants and how much we started with to the product, and we're looking at the products and we're saying, okay, the first one, iron, can produce 1.56, the second one, oxygen, can produce 1.80, so which one's limiting? Well, it's the iron that's limiting. It's the one that runs out first. And again, the limiting one is the one that determines how much can be produced, so we know only 1.56 moles of iron oxide is going to be produced in this reaction. Now, the second step then is to think about, okay, how much excess reactant was used, and then how much we have left over. And so here you're going to use stoichiometry to compare how much iron you actually used, using the 2-to-1 ratio of iron to oxygen, and then that way you can then subtract from what you started with to figure out how much you have left. And again, these are both very important things in the world of manufacturing and chemistry. Okay, so now we solved the second part of the problem. So here we took how many moles of iron that we actually used, because that was the limiting reactant, and then we converted that into oxygen, so that tells us how many moles of oxygen we used. Now, we started with 0.899 moles, and so if we subtract the two, we're left with 0.199 moles of O2 left. So that's basically what you have to do each time It is more work, but if you only solve through the moles, it's a lot easier than going all the way into the grams. And so you'll see what that means um, during future problems. So it's easiest to compare them together when you're looking at moles. And then finally, you could then convert that 0.199 moles of O2 into grams if you wanted to. All right, so here's the last sample problem, but this sample problem, we're going to go from grams of something we have to grams of the product, and so it's a little bit more extensive, and I'm going to solve this as, I want you to pause it, but I'm going to solve it, and I'm going to start and stop it so you can join in when you need to and, catch yourself up and then kind of go back to solving it on your own, because really solving it on your own is one of the most important ways to learn something. So I went about solving this problem the same way. I took the starting amount of each reactant and converted that into moles of one of the products. And again, in this case, I only have one product, which is FeO. I found out because FeO, or there's less FeO produced by the iron, that makes that iron the limiting reactant. I then took that amount that the iron made and converted that into grams, which was question number 2, grams of FeO produced. So we're going to keep going on and answering some more questions about this on the next slide. Okay, so if you further went on solving this problem, we wanted to figure out how much of what the excess reactant do we have left. Now, in this case, what I did was I compared it to a value that we already solved for, because again, we can use the mole ratios in any way. We already solved for moles of iron oxide, and so I can use that known ratio to convert that into oxygen, and so that's going to tell us how many moles of oxygen we used. And then from there, it was as simple as converting that into grams, or taking what we had started with, which was in grams, converting that into moles, and then subtracting these two values to figure out how many moles we had left. And notice how I'm circling the answer, because again, this is going to get a little bit more complicated, and there's going to be a lot more work, and some of us have better handwriting than others, me definitely on the lower side, and so you want to circle your answer so it's very clear kind of what you're doing and what your final answer is, keeping in mind the sig figs. And then finally, the very last question is just a simple conversion back into grams of oxygen. So hopefully this is making a little bit of sense. Some practice is really going to help solidify this topic. Before we're done, though, we're going to go into one more topic, which is more applicable to some of the labs. And so stay tuned for the next couple slides. Percent yield is a slightly easier topic than looking at limiting and excess reactants, but the idea is all of this math and stoichiometry is theoretically what we should get. Okay, it's based off the math, but that's never going to happen. Never, and I can say that almost with 100% certainty, because in life there are so many things that are happening during a chemical reaction that it's almost impossible to get it to happen to completion. And so we're going to just look at what was our percent yield. How much should have we gotten and how much did we get? So many people are used to just saying human error is the source of not getting everything we should. And a lot of times there is some human error, but now, especially in an honors level class, we want to take that a little bit further to figure out really what's going on, and to think about, besides the human error that we might have, what is the error in some of the equipment we have, and what is just in the chemical reaction that's happening that's going to prevent it from going into completion. Keeping in mind, in order for something to react, these molecules have to be in contact with each other, and so without, is every molecule going to be in contact with every other molecule? And so you want to think about some of these things when we're figuring out why the reaction doesn't go to 100% completion. So a couple examples here, you see, let's say, you're looking at evaporation, okay, or you're looking at some gas being produced, or maybe you're thinking about spillage. There are dozens and dozens of reasons you can have imperfections in a lab, and so we want you to try to really analyze those examples, and a lot of them will be reaction and experiment specific. So hopefully as you go through these labs, you'll think about these ideas. So a couple more vocab words to think about are what we said, theoretical yield. This is based off of the math. Okay, so via stoichiometry, that's going to tell us how much in theory we should be able to produce. The actual yield is what was measured in lab. So a data that was some lab data on a chemical reaction. Almost always it's going to be less than the theoretical yield. And as we go through the unit, we might talk about why it might look like there was actually more than the theoretical yield, and that should tell you maybe it's not 100% pure. So theoretical, based off the math; actual, based off the lab. And the math behind this is super easy, and it's exactly what we did with percent composition, where we have the part over the total. So you're going to take the actual amount divided by the mathematical amount multiplied by 100, and that's going to give you the percent yield. So see if you can answer these questions, and we can talk about the answer. Where do you find the theoretical yield? It's from stoichiometry. Where do you find the actual yield? From the experiment. Do you want the yield to be closer to 0% or 100%? Well, in a good lab, it's 100%. In reality, you might get something closer to 0, but it just really depends on the type of reaction. What's the equation for percent yield? Actual over theoretical times 100. So in the next 2 slides, there are a couple examples of what this would look like, and see if you can try them on your own, and then take a look at my example. Okay, so what you see here is I took the grams of the CaCO3 and converted it into moles, then used the mole ratio from the balanced chemical reaction to convert that into CaO, and then use the molar mass to convert that into grams. And I got, based off of the math, the theoretical yield to be 8.965. Plug that into the percent yield equation right here to get an 84.1% yield. So as you're looking at the math and how this problem was done, again, done the same way, started by taking the grams, converting it into moles of something else, and then grams of something else, and then putting it into the percent yield equation. And you look at that and it says 18.9% yield, that's not very good. And that's true, that's not a very good yield. But this is one of the most famous chemical reactions, and it's called the Haber-Bosch process. And ammonia is used for many things, and in this case it was used for the creation of bombs for Germany in World War II. But since then we've used ammonia for fertilizer, so it was created for bad and for evil. It was then created to feed millions. It's being credited for feeding millions, if not billions, of people. And so it's a very important chemical reaction. But why, the guy, Mr. Bosch, is given so much credit was he didn't invent the reaction, but what he did was he increased the percent yield from almost nothing to something that was a lot more respectable. I forget the actual number, but it's a very good percent yield now. And so we were able to take a reaction that wasn't efficient and turn it into a much more efficient reaction. So very important reaction to understand. And so if you dive into the history of it, you might find it very interesting. So I hope this helps. Hope you have a little bit better understanding of limiting and excess reactants, and then actual versus theoretical yield. So please continue doing some of the practice problems and come to class with questions.